The impact of diet on regulating energy intake typically focuses on the influence of macronutrient-specific foods or the characteristics of foods such as texture on satiety and satiation and the balance between appetite-promoting and appetite-inhibiting factors. Satiety and satiation encompass overlapping complex processes regulating acute short-term and chronic long-term energy intake and energy balance. These processes involve sensory, cognitive, and physiological effects. Foods and nutrients are proposed to influence energy intake through impacts on appetite regulatory hormones such as ghrelin, leptin, and glucagon-like peptide 1 or GLP-1, among others, and the neurobiological feedback between gastrointestinal and central brain mechanisms. Due to their varying thermogenic effects, i.e. the energy expended in digestion, macronutrients have long attracted interest for the potential role in promoting satiety. Could large variations in macronutrient profiles of foods influence energy intake through impacts on appetite hormones? Well, a recent interesting study from Hengist and colleagues, Professor Kevin Hall's research group, or former research group before he had to leave the NIH because of the Trump administration, but I digress, conducted an interesting exploratory analysis of data from a randomized crossover trial with adult participants residing in a metabolic clinic for 1 month, which compared the effects of 2 different diets, each consumed for 2 weeks. There was no washout period. It was 2 weeks on one diet, straight on to 2 weeks on the other. One diet was a low carbohydrate ketogenic diet consisting of 10% carbohydrate, 75% fat, and 15% protein, primarily based on animal foods. The other was a low-fat diet consisting of 10% fat, 75% carbohydrate, and 15% protein based largely on plant-sourced foods. Participants were randomized to the order of treatment, and all participants immediately switched, as I said, from the first assigned diet to the alternate diet after 2 weeks with no washout period in between. After each diet period, participants were provided with a standardized test meal at breakfast, which reflected the macronutrient content of their preceding diet they had consumed for the previous 2 weeks, and contributing 30% of their total daily energy requirements. There was a series of testing conducted after that test meal. The primary outcome was the subsequent ad libitum energy intake at lunch, dinner, and snacks, measured after the test meals, with secondary outcomes including postprandial GLP-1, glucose-dependent insulinotropic polypeptide, or GIP, peptide YY, total and active ghrelin, and leptin, all appetite regulatory hormones. The outcomes were presented as mean differences in the unit of measurement with standard error of the mean. As far as the results, 20 participants, 11 male and 9 females, completed the study. The mean age of the participants was 30 years and the average BMI was 27.8 kilograms per meter squared. The participants' BMI included 8 within normal range, 6 with overweight, and 6 with obesity. For the primary outcome of ad libitum energy intake compared to energy intake during the low-fat diet, during the low-carb ketogenic diet, participants consumed an average of 551 calories per day with a standard error of around 103 calories more total energy following the standardized breakfast overall. For specific meals, energy intake at lunch and dinner were respectively 244 calories and 193 calories greater on the low-carb ketogenic diet compared to the low-fat diet. There was no significant differences in energy intake from snacks between the 2 diets. However, following the test breakfasts, the actual mass of food intake in grams was significantly greater during the low-fat diet compared to the low-carb diet, both overall food mass and at the individual lunch and dinner meals. As far as the secondary postprandial appetite hormone outcomes, postprandial GLP-1 levels were significantly higher by just under 5 picogram per milliliter in response to the low-carb test breakfast compared to the low-fat test breakfast. Following the respective test breakfasts, postprandial GIP levels were also significantly higher by nearly 260 picograms per milliliter, again during the low-carb diet, and PYY was also significantly higher by about 15 picograms per milliliter on the low carbohydrate diet. In addition, active ghrelin was significantly lower by around 140 picograms per milliliter following the low-carb test breakfast compared to the low-fat test breakfast, while leptin was also significantly lower by just over 8 picogram per milliliters, again in response to the low-carb breakfast. And this is where it gets interesting. There was no significant correlation between postprandial appetite hormones and subsequent energy intake following the test breakfast for either the low carbohydrate diet, where we have seen all of these differences in postprandial measured appetite hormones, or the low fat diet. Keep a tab open on this because we'll circle back to it. It's the most interesting aspect of this study. As far as the strengths and limitations of the study go, the main strength of the study is that as a residential metabolic ward study, the parent trial from which this exploratory analysis was conducted had very strong internal validity and methodological rigor with full control over the participants' diets. In particular, energy intake was objectively quantified. Participants were randomized to the order of intervention. The diets were matched for protein content, but varied widely in the distribution of carbohydrates and fats between diets and in the food sources between the two diets, providing a strong contrast in the macronutrient and food-based exposures on the respective diets. The sample was well balanced as well for the sex of participants, and the results in the paper were well presented. But limitations in this trial should also be noted. As a crossover design with no washout period, carryover effects cannot be ruled out, and independence of the two diet periods may not be assumed. As an exploratory analysis, the outcomes were not pre-specified and the findings should be considered hypothesis generating rather than hypothesis testing. The sample size was small, and although that is inherent in 1-month residential metabolic ward studies, it does still limit the generalizability of the findings. The test meals were also delivered as a liquid, which may not represent the effects of solid food on subsequent energy intake or appetite regulatory hormones. And finally, acute effects of energy intake and other outcomes may not translate to longer-term impacts on energy balance or appetite regulation. Now, there is a reason why I think this study is still worth considering. Exploratory analyses may lack the probative value of direct hypothesis tests of pre-specified outcome measures, but they do allow for exactly what their name implies, which is to explore. And an interesting question presented in this study is, why is it, for example, that drugs that increase GLP-1 induce profound appetite suppression and consequent weight loss, but diet-induced increases in GLP-1 may not exhibit the same effect? Well, this particular study in exploring the data provided some insightful context on the relationship between dietary impacts on appetite hormones compared to GLP-1 agonists, semaglutide in particular, which you can see in this figure from the paper here. As you can see, levels of GLP-1 in either the low-fat or low-carbohydrate ketogenic diets pale by orders of magnitude to the dose response evident from either oral or injectable semaglutide. The average GLP-1 concentrations on the low-fat and low-carb diets were estimated at about 3.5 nanomole per liter and 5.5 nanomole per liter respectively. This contrasts with the dose of 1 milligram injectable subcutaneous semaglutide, which you can see in this figure, which achieved an average GLP-1 concentration of around 35 nanomole per liter. This comparison provided valuable context for the discordance between diet, appetite hormones, and energy intake in the present study. And that actually leads us to one of the most interesting findings from this study, as we alluded to in the results. And that is the lack of correlation between circulating levels of postprandial appetite regulatory hormones and energy intake. The low-carb ketogenic diet resulted in significantly greater energy intake following the test meal, despite significant increases and decreases, respectively, in appetite-suppressing and appetite-enhancing hormones. It should be noted that the lack of correlation between appetite regulatory hormones and energy intake was observed for both diets, i.e., irrespective of the levels of postprandial appetite hormones, there was no correlation with energy intake. This indicates that factors other than circulating appetite regulatory hormones influence acute energy intake following the test breakfast. There is actually a clue that lies in the data in this paper. Recall that the low-fat diet resulted in a greater volume of food consumed despite less energy intake consumed following the test meal compared to the low-carb ketogenic diet. In the parent trial, which we have covered in a previous deep dive in the Alinea Nutrition Education Hub, the energy density of the low-fat diet was about 50% less than that of the low-carb ketogenic diet. This combination of lower food energy density and greater food volume is now well established as a factor resulting in significantly less overall energy intake. The higher energy density of the low carbohydrate diet, coupled with other acute factors such as eating rate, likely explains why energy intake was higher on the low carb ketogenic diet despite the differences in postprandial circulating appetite regulatory hormones. And this is crucial for wider relevance to any studies that are looking at, as they say, objective appetite regulatory hormone. This study suggests that we should proceed with caution when extrapolating the findings of increases or decreases in appetite regulatory hormones to infer influences on energy intake and energy balance from dietary interventions, particularly where those effects are derived from acute single meal or single day interventions. While the exploratory nature of the present study means that a more direct test of this relationship between appetite hormones and energy intake will be warranted, the findings are also not entirely new. As we've also covered in this deep dive in the Alinea Nutrition Education Hub, the proposed chain between subjective appetite and appetite hormones and energy intake and body weight is tenuous. If we look at some recent research on the ghrelin antagonist hormone known as LEAP2, we can see that the effect of endogenous circulating LEAP2 levels are modest compared to the effects of intravenous LEAP2 administered in supraphysiological concentrations. This may be a crucial factor. It may be that diet-induced acute differences in appetite hormones are simply not of a sufficient magnitude to influence energy intake, at least in an acute context. Overall, it appears that factors other than circulating appetite regulatory hormones exert a greater influence on acute energy intake, which may include dietary energy density, sensory characteristics such as texture, eating rate, and energy intake rate, including energy density in that computation, and perhaps even time of day appetite variation factors. So, to conclude, how might we think about the application of a study like this? Well, as always with exploratory data, over-extrapolation is to be avoided. Nevertheless, it appears that manipulating carbs and fat alone will have little impact on appetite independent of food volume and eating rate. For sustained improvements in appetite or sustaining lower energy intakes for weight loss, the best practice guidelines of low volume foods, higher protein and fiber, and minimizing later energy intake all still appear to apply. So, as always, I hope that was helpful. If you enjoyed, consider liking and subscribing below and sharing with someone who you think would enjoy these long-form research breakdowns. Thank you.